Section 25.4. The vibrational fine structure of electronic transitions of diatomic molecules. Now let's look at the vertical electronic excitation and de-excitation of a diatomic molecule. The vertical axis is energy. The horizontal axis is the bond distance of this diatomic molecule. When this molecule absorbs a photon, it can be excited to the first excited state. And this is the so-called vertical excitation because this line is perpendicular to the horizontal axis. That means there's no change in the positions of the nuclei. Why is that? This is because the electronic transition is so fast. It takes roughly 10 to the power of negative 15 seconds. And during that short time period, the nuclei cannot move by a significant distance. For example, if a nucleus moves at 1,000 meters per second, then during this 10 to the power of negative 15 second period, it can only move 10 to the power of negative 12 meters, or 0.01 angstroms. The typical bond distance is between 1 and 3 angstroms. So that means the bond distance will change by no more than 1%. And therefore, we observe the vertical excitation. And also, during the excitation, the vibrational energy level may change. So right here, this new double prime is 0. That means this diatomic molecule is in the ground vibrational state. But then, during the vertical excitation, we should be looking for the maximum overlap between the initial and the final vibrational wave function. So you can see a peak here and a peak here. That's why this vibrational quantum number changes from 0 to 2 during this vertical excitation. So that means after the molecule is excited into the first excited electronic state, its vibrational energy level changes from 0 to 2. Eventually, this molecule may undergo the vibrational relaxation. That means the vibrational energy may be passed to surrounding molecules and to get here. And this is the ground vibrational energy level of the first excited electronic state. So again, there are two quantum numbers. This new prime, new double prime, those are the vibrational quantum numbers. And this 0 and this 1, they are electronic quantum numbers. So this is the ground electronic state. This is the first excited electronic state. All right, but then if you look at this number, this is the vibrational quantum number. So during the de-excitation from here to here, a photon can be emitted, but then this molecule will not get back to the equilibrium bond distance in the ground electronic state. Why is that? The de-excitation is also vertical. Again, during this de-excitation, the time period is so short that the nuclei do not have time to change their positions correspondingly. So this is a vertical de-excitation. From here to here, this molecule may undergo again the vibrational relaxation. The additional vibrational energy may be passed to the surrounding molecules. The Franck-Condon Principle states that the electronic transitions are vertical transitions because the nuclei do not have time to change their positions in an electronic transition. One simple explanation is this. The mass of electron is so much less than the mass of a nucleus. That makes this electron moves so much faster than the nucleus. The transition intensity is proportional to the overlap between the initial and final vibrational wave functions. So the overlap between this peak and this peak is very important. But this is not very accurate. I need to change it to the squared modulus of the overlap between the initial and final vibrational wave functions. So again, you may observe the transition from here to here, but the overlap is so small. I don't think you will observe a large transition intensity from here to here. From here to here, a bit larger, so you can see there's a more significant overlap. But over here, you have the maximum overlap between this wave function. You see this peak here and over here. So that's why mostly you will observe this electronic transition from the ground to first excited electronic state is accompanied by some vibrational transition from quantum number 0 to quantum number 4.